So I want to present some work that appeared recently, 2 months ago now, with Fabio, Nicola, Hotat, and Sakura, which I think they're all here except Nicola, which, by the way, I think Nicola is applying this year, and he did lots of fantastic work in this paper, so highly recommend it from my side. And the paper is about how do you incorporate continuous space-time symmetries into the framework of the SymTFTs. I don't know what I'm doing. All right. So yeah, continuous space-time symmetries was something, or space-time symmetries in general, was something that we were missing from the SymTFT framework. By now we understand very well how to deal with internal symmetries, but the space-time ones have been much more confusing. Certainly for myself, they were very confusing. And the problem is not completely solved by your paper, so I emphasized in the title, I emphasize here again, that we are dealing with continuous space-time symmetry, so the parts that are continuously connected to the identity. There will be translations and rotations, but I just don't know what to do with discrete space-time symmetry, so that's an important open problem. And I want to emphasize since the beginning, my motivation here will be, the way I will motivate the SymTFT that we construct will be from holography, but we don't really need holography for our proposal. It's just a way of motivating what we find. And to address from the beginning one of the questions that I think motivates this question, or at least if you're a high-energy theorist, arises very naturally here, which is holography exists. And we know by now, and Ibu just gave an excellent talk, how many of the things we see for the SymTFT appear in the holographic context, or many of the things we see in symmetries appear in the holographic context. And it's a natural question, if you're going to talk about internal symmetries, where is this in holography? So I want to start by addressing that point, which is one of the sort of biggest points that we need to understand. All right, and luckily we just gave a very nice explanation. Some of the aspects of ADS-CFT I will have to discuss. So I want to be brief, I will be brief. But I thought I would explain a little bit, particularly for those that don't work in holography, what I'm going to talk about, at least to give a bit of an impression. So when we talk about ADS-CFT, is the following statement, that we have some conformal field theories that can be described in 2 ways. One is using the language of conformal field theory. So you have a d-dimensional conformal field theory. Well, that's something you have. But sometimes it admits an equivalent, very different description in terms of a string theory or M theory on some space-time of the form ADS of 1 dimension higher. So if your conformal field theory is 4-dimensional, say, your ADS will be 5-dimensional, times some internal space, in Ibu's case was S5, for example, that completes the total space-time ADS times X to be the dimension that the string theory M theory expects. So if you're working on a string theory, you expect the total dimension will be 10. If you're working in M theory, you expect total dimension to be 11. And by now we know a lot of examples, infinite families of examples, and qualitatively different examples. But this idea works in a lot of generality. One way of thinking of this is that if you give me a CFT for some specific classes of CFTs, they sort of fix for you which string theory you're considering and which space-time you're considering. So probably the most famous example, and one of the best understood, is you start with a 4-dimensional conformal field theory, the specific type n equal to 4, SUN, Super Mills. So a theory that's very nice in many ways. Then this is equal, as a quantum theory, to a type to be in ADS5 cross S5. So what does that mean precisely? Well, first, one thing I'm going to do, which is often done in this context, is work in terms of the effective theory on ADS5, or more generally ADS D+1. So because the internal space is a compact space, what you do is you take every field and you decompose it into the harmonics, let's say, and you keep all those harmonics. This is not a truncation generally, but you keep all these infinite towers of fields. But you talk about ADS5, and this makes some of the questions a bit easier to answer. And then the basic dictionary was established by Gapser, Klebanov, and Polyakov, and Witten, and it goes as follows. Imagine that you want to compute some correlation function in the CFT. So let's write one that looks like this. First, I have to tell you where the CFT is in this dictionary. So ADS is a non-compact space, and it has a boundary in the physics sense. It means a conformal boundary, which is, if you're working Euclidean, SD or R times S d minus 1. You're working Lorentzian. Anyway, some space at infinity. And this is where the conformal field theory lives. So these are correlators of operators in a CFT put in a sphere. And imagine that you want to compute this correlator here. So these are insertions of operators that are space dependent. So the sigma 0 you get to choose. And the basic sort of component of this dictionary, understood since many years ago, is that you can compute this correlator if you can compute the string partition function with certain boundary conditions. So for each operator in the conformal field theory, you can find some field in the bulk. And if you put the right boundary conditions for this field, these two partition functions are the same. Yeah.
I want to clarify the notation. So phi 0 for you is a common constant.
No, it could be any asymptotic value of the bulk field. It could be the dilaton, yes, but it could be anything. Okay. So the previous formula was fairly general. It works also for internal zero-form symmetries. So the way this works is that if you have some global, let's say, zero-form symmetry on the boundary, CFT, on the bulk, what you see is a gauge field, a U1 gauge field. I'm going to call it A. And if you want to compute a correlator like that one of a conserved current, another current, times some A0 that you get to choose, you can do that by computing the partition function of string theory on ADS with boundary values for the gauge field being A0. Okay, so let me try to connect this to the things that we usually say. We like to think not of kind of superpositions of integrals of J. We want to think of integrals of J over some submanifolds. So effectively what I'm doing in this formula is choosing some A0, which is a delta function. I want to put some compact support. So let's say that I choose my surface where I'm putting the operators to be the boundary of some space. So this is on the boundary. Then A0, which is this delta function, you can understand it as the result of acting on the trivial A0 equal to 0 boundary condition with a gauge transformation, which is of this type. It's a constant equal to alpha inside the surface sigma and 0 outside. If you take the derivative of that, this looks a bit like a heavy side, right? So you get the delta function where you expect it. So we're acting on the boundary conditions for A with the generator of gauge transformations. So you want to find what the generator of the Gauss law is. And then you want to wrap it on DD. And so one thing I'm going to do in this talk repeatedly, I'm going to be thinking of the boundary values of my fields as a state on the theory that I will obtain if I quantize string theory, assuming I could, taking the radial direction as time. So as I go to the boundary configuration will be some sort of a state in my bulk theory. Okay, so that's what I want to do abstractly. Let me try to explain it in an example. So my strategy in this talk is going to do this for Maxwell, and hopefully you'll think, oh, this is obvious. And then I'm going to do it for gravity in a way that's very similar. So hopefully it's convincing that it's not crazy what I'm trying to do. All right, so let me start with this formulation of Maxwell theory, which is probably familiar to many, but let me explain it for a second. So in this formulation, I have two-form field. Let's say them in 4 dimensions, or in generally. So if A is a 1 form, D is a 2 form, so B is a D minus 2 form, and I write this action. Now you see that B appears quadratically in here. So if I integrate it out, you get an action which is the standard Maxwell action for A. There's a little subtlety here, which is that there is a one-loop determinant, which is studied in this paper by Witten, but it will not play any role in what I'm going to say. A different thing that you could do is, if you notice that A appears linearly, you could then integrate it out. It's a Lagrange multiplier that imposes that B is pure gauge. So B is D of some C. And this becomes Maxwell theory now, but with C. And if you do the integration out, you'll see that the coupling is 1 over E squared. The E squared appears in the opposite convention as usual. So this is one way of proving S-duality, if you want to do that. In this talk for gravity, or more generally for non-abelian theory, the thing that we generally do is we work with the Gaussian integration side, and we don't do this integration of the Lagrange multiplier. Okay. So we want to understand how to act with gauge transformations on A. So I want to take some A0, and send it to A0 plus alpha delta, or some sigma, which is the boundary of some t. Right? So I want to do this sort of insertion of the symmetry operator that we generally like to do. Okay. So in this formulation, it's clear what I need to do, right? The Gauss law is generated in this case by dB. That's the analog of the divergence of star of f that Ibu was already talking about in his talk. So here, that's what generates gauge transformations for you. Or if I want, because D is it's a manifold, better. Because, oh, sorry, the D minus 1 should be in the sigma. Because sigma is the boundary of D, I can write this Euler-Stokes as the integral of B over sigma. Now, I'm sure many of you are thinking now that I'm overcomplicating things. There's a different way of doing this, of course, which is noticing that B is the momentum conjugate to A. So if all I'm doing is translating A, what I do is act with B, with the momentum. And that's true. There's nothing wrong with doing that. But when it comes to gravity, this point of view in terms of gauge transformations will be useful, and it will give us some valuable intuition. Any questions so far? Please feel free to interrupt. I mean, this is in no way sort of a closed talk. There will be many questions that appear during the talk, and I'll be very happy to discuss them. Okay, so one thing I want to emphasize as an important subtlety. If I look at this description of Maxwell theory, notice that the would-be B going to B plus d beta gauge symmetry that you'll have in pure BF theory is broken by the B wedge star B term, which is not there, it's not gauge invariant. So because this term B wedge star B is not gauge invariant, your gauge group is smaller, and that means that you can have more gauge invariant operators. So in particular, the operator that I'm trying to construct, e to the alpha integral of B, the thing that shifts the background as I want, the generator of the one-form symmetry, of the zero-form symmetry, is gauge invariant. And I don't have to worry about having to attach a surface with dB. There's a bit of a difference with respect to what we generate in BF theory. So if I wrote just the second term, BF theory, we would immediately say, well, I shouldn't write this operator because it's not gauge invariant, at least when e to the alpha is different from 1. But in this context, what we want to do is understand these symmetry generators, these U1s, or whatever they are. Then this is important to keep. But otherwise, keeping in mind the subtlety, if what I want to do is understand how do I act on boundary conditions, I could forget about the first term. It doesn't really do anything apart from allowing me to introduce some more operators than what I would naively do. The shift will happen anyway, whether the first term is there or not. B is the momentum conjugate to A, whether the first term is there or not, and so on, so everything works. So one way of motivating the statement I'm going to make is that, well, I'm going to look at this theory, but I'm going to discard the first term if all I'm interested is action of symmetry operators acting on the boundary. Yeah.
I mean, so rather than discarding the first term, you could replace star B with its own differential field, and then relate the two curvatures. So you'd still have a topological term there. Is that not? Yeah. Why wouldn't you do that from a physics point of view? So you make the action you make the action topological, but then you impose on the fields a condition that one is the curvature of one is the curvature of the other. So you have a topological action, but a non-topological.
Yeah. Yeah, you could do that. There's a physical reason to actually do this, the sending the E to 0, and it's holography. Ibu, I think, mentioned there's a scaling argument that if you are going to act on infinity of ADS, the natural thing to do is sending E to 0.
That sends a curvature to 0, but there could still be a topological. You see what I mean?
I'm not sure I do.
Oh, sorry. I mean, we can discuss after.
We can discuss later, yeah. Yeah, I'm not sure. Okay. So something which is similar to this was emphasized in a recent paper by Ye, Luo, Tian, Wang, and Sun. And they argued, I think, convincingly that really when we talk about the SymTFT being a BF theory, it's in some sense, one reason to motivate it requires a bit less information that we generally give. So we often say that in holography E goes to 0 because of some scaling argument, as Ibu was saying. But for many symmetry computations, like the ones I'm going to be doing, the thing that really matters is that B acts as a shift of A. Yeah. Mm.
So after you take E to be 0, you impose the beta on H.
No, I would like to have a theory in which I'm not imposing that.
Or not
So
imposing
if you look at the papers where they propose a SymTFT for U1 symmetry, for example, they put an R U1 gauge group, and the R is precisely basically to kill that sort of symmetry. No, then you're not. So the B, which is star B, gives you a regulator for this theory. So the way I think of this is that I'm working in the limit in which E is very small. And at the end of the computation, I send it to 0. Okay, and precisely what you are saying, there's a number of subtleties with taking strictly the E goes to 0 limit. One paper that discusses them quite nicely is this paper by Cattaneo and collaborators, Alberto and collaborators. Yeah, so it's something to keep in mind. When I make some statements I make, at least the way I think of them is in the limit in which E is tiny but not strictly 0, otherwise some of the things I'm saying, I don't know how to define them carefully. Okay. All right, so what we want is some sort of BF theory, but we want to allow ourselves to include the operators that we actually want, the E to the alpha. And this is done in these papers. And subject to the subtleties above, this has already been explained, what I just told you in papers by Federico, Michele, Ruben, lots of people in this room. And although I won't review it in detail, the discussion extends, changing what you need to change, to non-abelian internal symmetries. So there's some important technical subtleties that were in fact with the construction of the B operators that generate so these operators, the non-abelian generalization of these operators is quite subtle. But it was worked out, in fact, in this paper by Cattaneo and Rossi. So you can just read the results and they will tell you how to construct the analog of the B operators. So we use that in our paper. Okay, so that was something that most of you know very well, I'm sure. But the thing I want to do here is to talk about the space-time symmetries acting on the d-dimensional CFT. So you have a d-dimensional CFT, the group of symmetries I'm talking about, the continuous ones, is the conformal group, which is SO d plus 1, 1. So I'm working the Euclidean at the moment. And what's the expectation from holography? Well, the expectation has been known before holography. before ADS-CFT at least. So Brown and Genot told us that the conformal group on the boundary arises from the boundary behavior of the bulk gravitational sector. So it told us how to reproduce the full conformal group in 2 dimensions from gravity. And I could include a very long list of papers here which show that if you're asking for space-time symmetries on the boundary, you're probably asking about gravity in the bulk. And that makes sense. So most of the things we know how to do in holography in terms of symmetries have been in terms of branes or in ADS gauge fields, but not quite the graviton, not quite the metric. So the part that we are missing on both sides is gravity on holography and space-time transformations in the SymTFT, so it stands to reason for this and many other reasons that they should be related. So let's try to follow the same strategy. I'm going to try to write gravity in the bulk as a BF theory for the conformal group, maybe with some corrections, like the B wedge star B that we had for Maxwell. And then try to argue that the effects of space-time transformations on the background geometry of the boundary can be understood in terms of operators in the BF theory. If I can do that, then this will suggest that I can take some sort of BF truncation in the same way that I set E to 0 before, keeping in mind the subtleties, and obtain the SymTFT for the gravitational sector. So which cases should I start with? Well, there's a big distinction between even and odd dimensions for the CFT in this context, which is that for even dimensions, you have a conformal anomaly. And understanding the conformal anomaly is complicated. So we make some progress on this in the paper, but I thought it would be too much for this talk. It's quite technical, but you can read about it in the paper. I'm more than happy to answer questions. About the basic idea, maybe I should say, you can include some of the conformal anomalies if you add to the BF theory some Chern-Simons term, as you might expect. It's an anomaly. So Chern-Simons are perhaps not very surprising, but the details are rather tricky. Okay, for odd-dimensional CFTs, odd-dimensional quantum field theories, the bulk will be 2 dimensions, 1 dimension higher. And there actually this sort of guess works quite nicely, and this is very well understood. If you don't have pure gravity in the bulk, you have something known as JT gravity. But JT gravity is famously, at least at the Lagrangian level, it can be rewritten as a BF gauge theory for SO 2,1. Here, I was trying to be careful with the words. So one of the themes that will be appearing a few times in this talk is that even just because I can rewrite one Lagrangian into another, there are some important subtleties. For example, when we do Einstein gravity, we don't allow the metric to degenerate, typically some of our non-degenerate metrics. When you work in this kind of BF formulation, there's no reason to impose that. The metric will naturally degenerate. So anytime you work in the first order formulation, you have to worry about this. And we do worry, and as I will explain, there's something very interesting going on in our construction with that. Okay, so let's go to the JT gravity. I take it as solved, but you might argue, if you're a physicist, that, okay, that's all beautiful, but JT gravity is topological, there's not really a graviton around. So let's try to do a theory which actually has gravitons. Which better theory has gravitons than 4-dimensional gravity? So let's do that. So let's work with 3-dimensional conformal field theories, and we have a bulk which is described by gravity on ADS4. And the job is to try to write this bulk in terms of a BF theory plus corrections. Now, notice, those of you who have worked on gravity before are probably thinking, well, I know this is Plebanski, but I want a bulk gravity, which is a bulk gravity for the conformal group. So in this case, a gauge theory for SO 4,1. Not the Lorentz group. Gravity is famously a gauge theory for the Lorentz group, but I want a bigger gauge group. Yeah.
If you go to 11 dimension, you will have the semi-sphere as the second vector. This exotic sphere then can be seen, correct?
You mean the internal S5?
So if I stand, you have another factor of S7, right?
Yeah, it is 5 crosses 5 or something.
Different small structures.
Yeah, yeah.
Did that have some reflection?
Oh, that's a good question. Yeah, I don't know. Smooth structures on the S7 and ADS4 crosses 7. Maybe somebody knows. I don't know. Yeah, that's a good question. Yeah. In this example, I'm going to be working on the internal space. No, you're completely right. I don't know.
Will be interesting.
It will be interesting, yeah. Más o menos, I don't know. Yeah, it's a very good question. All right. So in this case, there's a formulation of general relativity, which is actually very well suited. It's not the standard BF that you find in Plebanski, for example. It's a BF reformulation done by those authors there of McDowell-Mansouri gravity. Now, let me just give it to you. Here it is. I claim that this is classically, at the level of the Lagrangian, the same thing as Einstein gravity in the first order formalism. It doesn't look like Einstein gravity, the first order formalism, but I promise it is. So what are the fields here? Well, first of all, we have a gauge. I hesitate to call it gauge group for reasons I will explain in a second, but I have indices I, J that take values in SO4,1. I have a connection on a principal SO4,1 bundle, A. By this, all I mean is that this is one form, takes values in that joint. I have a field strength constructed as usual. And B is a two form that takes values in that joint again. One extra ingredient here is that I'm including a VM, which is a zero form, it's a function. It's a vector of SO4,1, so it has one index. And I'm going to take it fixed. It's something I get to choose. There are papers that try to make this dynamical. For today's discussion, I just want to keep it chosen. Okay. So I'm going to choose it in a generic non-zero way for the moment. Now, using the symmetry of the problem, any non-zero vector I can put on that form up to scaling. So let me write it like that. I have suggestively written it in terms of lambda, which is going to be a cosmological constant, and G Newton of ADS. But for the moment, that's a choice. It's just a number I pick. So if I look at this action with the V, I notice various things. But one is that B appears quadratically. So let me integrate it out. If I integrate it out, I obtain this kind of action that was written by McDowell and Mansouri. And the fact that V has components only in the fifth direction, it means that the epsilon there fixes one index. So effectively, I take the I, J, and KL to be in SO4, not the full SO5, because of the epsilon. So I'm going to use this convention in which even if I live in SO4,1, when I write the uppercase indices live there, but the lowercase mn indices live in SO4. But otherwise, it's just the same field. So when I write f hat mn, just means the mn components that go from 1 to 4 of f itself. Okay? That's the big notation. Yeah. Mm-hmm.
So for the case of JT gravity,
Mm-hmm.
that's not exactly equal to Einstein-Hilbert.
Yeah, correct. Yeah.
There's an extra ingredient given by the dilettante field.
Yeah, correct.
Is there similarly an extra ingredient here?
No, this is Einstein gravity.
This is just Einstein gravity. Okay.
That's true. There's an extra twist I will explain in a second, but the dynamical fields are Einstein gravity.
Are there background fields that are?
No, let me just explain that in a second.
Okay.
Locally, it's really Einstein gravity.
Okay.
Okay. So nothing fancy here. Just complete the square, basically. And to recover Einstein gravity, what I do is, as we do, for example, in three-dimensional Chern-Simons, many of you will be familiar with this, I take the 5m component of A, of the connection, to be the Vierbein, and let's get the Vierbein, and the spin connection is the other components of A. All right, so I put this A into the formulas, I expand, I work a little bit, and I end up with this action in here. Those of you working in gravity will recognize this is the Einstein-Hilbert term in Palatini Cartan, so the formulation, first order. This is the cosmological constant term. And there is a term that I have omitted. If you expand, you'll get also an R, which R term, which is the Euler density. So this is the only twist here. It has a topological term. But otherwise, yeah, this is just Einstein gravity written in a funny way. Let me make a comment, maybe. The term that I have omitted here is quite important for some applications. For example, as explained very nicely in these papers by Weiss and in the book by Krasnov, if you are doing holographic renormalization, or renormalization of ADS in general, you get an infinity from the action of ADS in ADS space, and the topological term is such that it sort of kills this infinity. So it helps a lot with making things finite. So it does have some effect, but not locally. Okay. So now we have some description of gravity in the bulk, but I want to understand how these sort of bulk degrees of freedom couple to the boundary CFT. And that was explained in a paper by Fradkin and Seilin, probably, where what we do is we take the A0, and now we expand it in components in terms of the algebra, the conformal algebra. But now I'm looking at how these elements of the conformal algebra transform under the Lorentz group of the boundary. So the boundary is three-dimensional. SO4,1 has a sort of Lorentz group inside, which is a rotation group, if you want, SO3 in this Euclidean setting. And here the indices, the A, B indices, refer to this SO3. Okay, that's what we're thinking about there. So when you have an A0, which in complete generality you can expand in this way, so the generators of the conformal algebra of SO4,1 can be split under this subgroup into rotations of SO3. These are translations, these are special conformants, these are dilatations, so our familiar generators. And when you expand an A, the way this coupled to a CFT is that this gives the dry bind in this case, this gives the dilatations, and so on. I'm sorry, this is essentially the spin connection, up to a small correction. All right, so we know how to couple things to the boundary once we have a boundary value. And as you'll notice, this is not quite the way quantum field theory with symmetry SO4,1 will couple to this data. Generally, it will couple as a spin connection, but this E will appear in the kinetic terms. This thing will work in the kinetic terms, so the couplings are very different. The conformal theory couples very differently. But all we want to do in the SymTFT is to make sure that when we act with the symmetry that we are after, translations or rotations, or whatever it is, this background transforms the way it should. That's an important point. Much of what I'm saying works for any non-abelian BF theory, but some things are specific to gravity, but they are more in the side of interpretation than calculation. Okay. So, at least in this case of CFT3 for the gravity, sorry, maybe it's a point I would like to make. I will argue in a second, and in the next section, that I can understand the translations, for example, as an action on A, because I want to act on A and my canonical structures, same as in Maxwell, B squared plus A dB. If what I want to do is shift A, which is what I will want to do, then I can restrict myself to the BF sector of the McDowell-Mansouri theory. If I go back to the BF sector of McDowell-Mansouri, there you go. What I'm saying is that this term is enough to generate the symmetries that I care about in the CFT. And this term I can discard when it comes to generating the transformations. There's also a dynamical argument, in the same way that in holography you can argue that the branes become topological and so on, and we give this in the paper, in which we argue that if you look at the effective metric on the boundary, effectively this VM goes to 0. One way of saying this is that this combination, lambda G Newton close to the boundary, becomes 0. Maybe one sort of intuitive way of understanding that is that in holography, gravity decouples on the boundary. Gravity does not act on the boundary. So from that point of view, you can also sort of try to convince yourself that the most important term is going to be the first one. Okay. So I made a proposal for the BF theory. So it should be the BF theory for the conformal group SO4,1. Before I go on, let me try to clarify a couple of things that were confusing. I mean, they have been confusing for me at least. So one thing I already discussed, we're working in the first order formulation of gravity. And there's no good reason to keep Vierbeins non-degenerate. And then you have a problem of interpretation. What does it mean to couple a CFT with a degenerate Vierbein? So we'll encounter this problem very starkly in a minute. Another interesting problem, which is related to what happened in Maxwell, is that if you literally, if you keep V different from 0, then you don't have the full SO4,1 as a gauge symmetry, in the same way that you didn't have the B shifts as transformations in Maxwell theory. That was good in Maxwell because we went to the physical photon, not the gauge mode. So the same thing happens here. The graviton exists because we have broken the gauge symmetry is not the full SO4,1. The graviton becomes pure gauge if I take the strict limit. So in that limit, the theory is topological. There's no dynamical excitation precisely because the gauge group has been enhanced. In the same way that the B shifts will kill the photon in the pure BF limit of Maxwell. And you might ask, well, we know diffeomorphisms are the thing that make gravity very special. So what are they in this theory? Well, they're not gauge transformations in general, but I will argue in a second that in the limit that V is equal to 0, the full group of diffeomorphisms can be encoded in terms of gauge transformations. So all diffs in this theory are gauge transformations. So now we have a gauge theory of diffeomorphisms.
Translations?
Yeah.
Really? But what if I have two nested ones and I have a translation which pulls one outside the nesting? Then how could this be fully topological? This doesn't make sense.
Yeah. Can we discuss this when I come to translations? It will be 3-4 more slides.
Well, this seems to be the main part of your story, but okay.
Yeah. I'm not going to evade the question, but it's in 2 or 3 slides. Okay. So let's test the conjecture beyond holography. And basically, our paper is about this. We have the motivation in terms of holography, which I just gave. It seems reasonable to think in this way if you want to give the SO4,1 BF theory as a prototype as a proposal for the SymTFT for translations or rotations or whatever it is. But the proposal itself doesn't require holography. So the proposal is that you have a d-dimensional CFT with d odd. We conjecture the SymTFT is given by the non-abelian BF theory for the conformal group. If you have a d even, then you have to add Chern-Simons with respect. Okay, so let me start by identifying the conformal symmetry generators in terms of the BF theory for translations, for example, and then I will try to address Jonathan's question. I'll do it in flat space. So let's study the action, the non-abelian BF action. Here, F is the field strength for A. So we have an equation of motion, which is dA of B is dB plus AB. And in general, as before, we take the coupling of the bulk fields to the CFT to be of this form. What this means is that when you're writing a CFT, you will want to couple to the spin connection and the Vierbein and so on. So this is the expansion of the A field that allows you to couple. Now, if you want to act on this A by shifting, the natural thing that acts on A is B. So I've expanded B here in terms of the dual generators of the algebra. So LAB is dual to L and so on. And JAB are whatever dimension B is as a form. So it's typically a D-2 form. These are forms of that degree that have indices in the dual algebra. Right, so we have the equation of motion, dAB is equal to 0. So if you expand it in terms of your components, this is what you get. Perhaps not very transparent, but after a little bit of work, let's do it in flat space, the equation simplifies to something that looks much more relatable. So we found these 4 equations. We have 4 conserved currents. And if you have 4 conserved currents, well, you can construct 4, well, it comes with indices, so you can construct these symmetry generators. I have called them P, J, K, and D in analogy with the generators of the conformal algebra for different reasons. One of them is that if you look at the standard expression for the conformal generators in CFTs, they take precisely this form. So we expect them to be the standard generators. Just in terms of notation, I have called TA the Hodge star of TA. Now, one thing that was confusing, was not familiar at least, was that these generators depend explicitly on your coordinates. So there's a subtle distinction, well, it's not very subtle, there's a distinction between operators that are invariant under deformations. You have integral of J, and you want this to invariant under small deformations. What you want is that dj is equal to 0, so d of the put inside is equal to 0, that's true. That's not necessarily the case whenever you have explicit dependence on the coordinates with commuting with the energy momentum tensor. If you recall basic quantum mechanics, you have that the total derivative with respect to time is the commutator with h plus the explicit derivative with respect to t. So these operators can fail to commute with the generators of translations, for example, the energy momentum tensor, while still being topological in the sense that they're the integral of a conserved current, dj is equal to 0. This goes a bit towards addressing Jonathan's question. Yeah. D equal 1.
Well, you said E is an odd number, so the minimum is 1.
Yeah, that was the case for JT theory, JT gravity. Yeah, so.
Does work for minus 1?
Oh.
Well, it's not quantum mechanics, so
That,
in principle also.
yeah. Well, I can tell you, it sort of works for D equal to 0 in a funny way. In that case, you don't have an anomaly, but the bulk theory can still be written in BF form. You want something which is a boundary bulk system to make this story. So D minus 1, I wouldn't know what it means. But D equal to 0, it makes sense and it works. It works in a bit of a silly way, but it works. Okay. So yeah, so part of the mystery comes because of this explicit dependence on the coordinates, but okay, you can understand that. We sort of try to argue the most confusing thing of this whole story, which is, up to me at least, okay, we want to write this picture, right? We want to say, well, we have a SymTFT, we have our lines, which are chart operators, we want to act with something which is a translation, it runs one of them, and it should move this one, but not move this one. How does that happen? Sorry, I should emphasize. Remember that, emphasize one thing, not to lose track of the notation. My T is the dual of P. So this is the thing that's going to be dual to P, the thing that's going to generate translations. Okay? So whenever you see a T, you should think, this is the direction that generates translations. So for example, if you look at these generators, this P generates translations, this J generates intrinsic rotations plus the rotation that depends on how far along you are from 0. And similarly for special conformal for dilatations. Okay, so yeah, let's address this head on. We have this generator, which is T times P dual, so we choose B to be that. And we choose A to be, simple case, yes, flat space, so is E times P. So in this case, Vierbein in the P direction, Vierbein is always in the P direction, so yeah, a Vierbein. And now let's see how B acts on A. Well, B and A are canonically conjugate, so if you act with this P symmetry, which is an exponential of this P is simply T times P star, you get a delta function localized on wherever these two things intersect. So that's the delta function, and of course you translate in the appropriate direction. So the translation operator, exponential of x times P, written as the exponential of this thing, acts as a shift of the Vierbein in this way. So where's the picture here? If I go back to this picture, this is the Dirichlet boundary. I have pushed my symmetry generator to this boundary, and what it has done, as symmetry operators do, it has changed the Dirichlet boundary here. It has changed in particular what the Vierbein is. So let's draw a cartoon here. Take, for simplicity, flat space here. I'm going to parameterize the metric so the RD in the following way. I have a transversal coordinate, which I'll call X. Then there's the plane where the symmetry operator lives. I'm calling that Y. And I have 2 points, 2 insertions of operators, which are separated by the defect. Okay, and I choose the generator to implement translations in the X direction. So it wants to move in the inside of here. It wants to move it in this direction, say. Okay. But everything I have proved so far is that it changes the VL-bind. So are these 2 things compatible? Well, the distance between these 2 points is the integral of the VL-bind. So by inserting this operator, I have effectively put them farther apart. That's the sort of, I think, a consistency check. This makes sense. But let's go back to the story about gauge transformations I was talking about in the beginning, which I think is a more beautiful way of understanding what's going on. So let's write my translation generator, which is the integral of t on the surface, on the line that I was drawing, as the integral of dt on some b, where the boundary of b is sigma. So for me, b is this side of the board, whatever is to the right of this line. Okay. I'm writing line integrals and integral over the half plane. Okay, so dtx equal to 0, this is a constraint in the BF theory. This is a B field, so this dB equal to 0. That's a constraint. So it generates gauge transformations, goes back to Dirac. And you have that the Poisson bracket between A and P generates this specific gauge transformation, where lambda is the gauge transformation you have. In this case, is constant on the right side of the board. It's like in the case of the symmetry generator I had before, I had the constant inside and 0 outside. So same story. So I reproduce the same result, of course, that acting on the VL-bind, this transformation introduces a delta function, but now I'm thinking of it in terms of a gauge transformation of the BF theory. Now, why is this useful? That's because BF theory has this very beautiful property that the action of a diffeomorphism on one forms, say, in BF theory can be understood also as a gauge transformation. So how does this go? The action of a diffeomorphism on a one form is given by acting with the Lie derivative. The Lie derivative you can write using Cartan's magic formula as the interior product times the exterior plus the exterior times interior, as I do here. And in the non-abelian case, you can add the extra factors to go into this formula. It's a little exercise. So what you find is that in non-abelian theory, or in general, the derivative acting on A can be written as the interior product of the field strength plus this term here. Now, in BF theory, the field strength is 0. So you're left with this term in here. And you'll notice that this is a gauge transformation with parameter interior product with respect to the vector field that generates the diffeomorphism with the background field. This means that in BF theory, any diffeomorphism can be represented in terms of a gauge transformation. And I know how to do gauge transformations. I act with operators from the back. I didn't give the proof, but you can easily argue that the same thing is true for B. So in the whole theory, diffeomorphisms can be replaced by gauge transformations. Annoyingly, I don't know how to prove this infinitesimally in the non-abelian case. In the paper, we have a proof up to degree 3, I think, 4 maybe. We proved it to ourselves to degree 5, so it's true, but I don't have the proof. If anyone knows a proof, please let me know. I'll be very curious to know. Anyway, it seems to be true. In our case, we can take a converse of this statement. So if you have a gauge transformation, so you have a diffeomorphism. So we have so far a gauge transformation coming from the insertion of the symmetry operator. Now, in this case, you can find a diffeomorphism that undoes this gauge transformation. So it takes the metric between the 2 points to be the same metric you had before. But you have to pay a price, which is that you're acting with a diffeomorphism on your theory, and everything gets carried along. So in fixing your metric, in coming back to the flat metric you had originally, the standard metric you had originally. The price you pay is that you have to shift this point with a diffeomorphism. I like to think, this is a little bit poetic, I don't know, but it helps me, that I'm introducing a little bit of space and acting with this operator. So yeah, you can stretch it out, but then you have moved the points that were on the side. Okay, so this is where the reason for my comments about the linear story, the linear gravity. There's a price you have to pay here, and I don't know if this is I don't think it's an issue, but it's definitely something I don't know how to solve properly. So far I've introduced how to separate points, inserting these operators. I introduce a bit of space, but what happens if I remove a bit of space, if I try to bring the points together? Well, one option you can do, if the points are far enough apart from the thing that brings them together, is to smooth this out. So instead of having a singular diffeomorphism, something that takes E and takes it E plus delta at some point, make it smoother. It's a gentle delta, and that's fine. That you can do. So effectively what you're doing here is something that also was in Ivu's talk. You're effectively smearing the operator insertion to get something reasonable. This seems harmless. But there's no good reason to do this, and in some cases it's sort of unavoidable. So in the context of symmetries, very often we want to think of symmetry generators not as smeared objects, but as delta functions that we sort of put in one specific cycle. And if you look at the details, there's always going to be a little region where you run into trouble. So if I put a symmetry operator that moves points away in this direction, well, this is fine here, but in here it's going to be bringing points together. So there's always a little region where you have to explain what's going on. You may be lucky, and maybe your operator insertions are far away that you can regularize, but in general, I don't know how to answer this question, which is, how does the conformal field theory react to this kind of regions that arise in this process? I think it's a very interesting question, and I don't know how to answer. Okay. Oh, it's very yellow. Okay. Okay, great. So maybe, yeah, I can finish quickly, I think. So, all right, so one of the checks we did, and let me describe this quickly, in addition to try to understand these conceptual points, is how do we get the effective dilaton action? Does it come when you break the conformal group to the Lorentz group? So there's a very well-known construction known as the CCWZ construction or coset construction that tells you the answer, it tells you what the dilaton action is. So we sort of try to reproduce these results from the point of view of SymTFT. We have the right SymTFT, we should be able to reproduce these results, and we can. So first we have to understand how to understand SymTFTs, spontaneous symmetry breaking from the point of view of the SymTFT. And I should remark that there's a really nice paper that appeared simultaneously with us, where they do a lot of, they understand this problem very well. And one thing I want to emphasize also is that I'm abusing language. When I say spontaneous symmetry breaking, I mean having a nonlinear realization more than actual spontaneous symmetry breaking, which would require a non-compact space. If we want to understand non-compact space, I have to understand SymTFTs with corners. There's progress on this, so it seems doable, but we didn't do it. And the paper by Michele and collaborators does do more of this. Okay, so let me explain quickly what happens for the Maxwell theory, for the Goldstone boson. So as we all know, the photon can be seen as a Goldstone mode of a spontaneously broken one form. So we'll start to understand that in the SymTFT. So in this case, we take the BF theory to be RU1, same as in these papers. And we put two boundaries for the SymTFT, one which is Dirichlet. In our case, or in this case, for simplicity, I'm assuming that the background is flat. If you want to make it not flat, there's proposals. So we put this on the left, the Dirichlet boundary, that fixes some background for you. And on the right, we put a modified Neumann condition that introduces a gapless mode, which is going to be our Goldstone, basically. So we can put that on the right, on the left, close the sandwich, and well, there's some subtle details and kind of glazing over here, but they're all explained in the paper. If you close the sandwich, you end up with the effective action for a Goldstone boson coupled to a background. Basically, is this term we have replaced A with the result from the left minus the difference, which has to be a gauge mode in BF theory. Okay. So this story generalizes to the non-abelian case. Let me tell you something curious, and then I will finish. One of the things that doesn't generalize very easily to the gravity side, to the conformal side, is here I'm using the Hodge star. I'm trying to create gravity here. I don't have a predetermined gravity for me. I don't have a background for me. So where on earth I'm going to materialize a Hodge star from here? Well, the thing I can do is on the left boundary, when I'm putting the Dirichlet boundary condition, this is going to be the metric that the CFT ends up coupling to. So it is there. It's just a component of A. So I can still write my formula, but introducing this sort of very nonlinear operation, we wrote it HOD of A, which works in the following way. If you give me a form, like a 2 form or something, I expand it in a basis for the cotangent or suitable power of the cotangent space, generated by the Vierbeins that appear in A. So this is an A-dependent decomposition. And once you give me the basis elements in this A-dependent way, then I can define a Hodge for these basis elements. So the metric is the number. Oh, sorry. Anyway, so if you put the star, instead of a normal star, this star depends on A, and you put the crank and so on, you end up with the action that you expect. So conclusions. To construct a SymTFT, we need to understand first non-abelian symmetries, and there has been lots of progress. One of the key things was already in a paper by Caterina and Rossi more than 20 years ago, and recently we have realized how to use this in the SymTFT. There are conceptual issues which I have tried to explain, but I'm more than happy to explain after if anybody was unsatisfied with what I said. And well, we propose a theory that seems to work, up to what we could check. And this is what I wrote this morning. I could have written many more pages. There are lots of open problems, but I think now we're in a good situation. We have, instead of one big problem that I didn't know what to do 2 years ago, now we have lots of small problems that seem all approachable.